Good day, everyone, and welcome to our webinar presentation. My name is Adam Harris, C-Therm, CEO for C-Therm Technologies. Very pleased to welcome you here today to our feature application webinar on looking at different novel construction materials and how we can use accelerated transient methods for measuring thermal conductivity, how important thermal conductivity is in the performance of some of these materials. Today's webinar presentation should run for approximately 1 hour. We've got a lot of material content to get through. I'm going to jump into this fairly quickly, but I want to welcome you to the webinar presentation. As we go through it, please make use of the chat box feature. Feel free to ask any questions or comments. If we're not able to respond or address those in real time, we will reserve some time at the end for a Q&A session. So I'm the warm-up act on today's presentation. I'm going to be pleased to transition this to Arya Hakimian, application scientist on our team, who's done a great job curating some different highlights from around the world of how different researchers are characterizing thermal conductivity of some very novel different types of material for construction. We're going to hear about phase change material. We're going to hear about aerogels and bio-based insulation. All kinds of different novel materials to use in construction. So without too much further ado, I'm going to jump into this now. We are recording this webinar presentation. You will automatically receive a link to it. So if you would like to replay any of the content, you can do that. You're also welcome to share the recording with any of your colleagues or friends. That's certainly something we encourage, and provide an easy way to do that in providing you the link if you registered for this presentation. So with that said, I'm going to jump in and just provide a little bit of background on who C-Therm Technologies is. I see a lot of different names, and one of the great things about these types of forums is we're able to draw from all over the world. So I see some folks from Europe, throughout the US. Looks like some folks are staying up very late in some parts of the world to catch this, and really want to express our appreciation for this. Some of you have known us for a long time. Some of you are maybe less known to C-Therm, or vice versa. You're not as familiar with who C-Therm is as an organization. So I just want to take an opportunity really quickly to express who we are as an organization. We're a Canadian tech company based on the East Coast in small little town called Fredericton, New Brunswick, which houses one of the top engineering universities in Canada. And our technology grew out of that University of New Brunswick about 20 plus years ago. And our whole reason for being, our raison d'etre in life, how we help customers around the world, is in simplifying thermal conductivity testing for the materials of tomorrow, helping accelerate the testing, make it possible to more easily test under better representative conditions. That could be under high pressure conditions. It could be in different atmospheric conditions, high temperature, low temperature, under compressive force loads, high humidity. What we really strive to do is provide a platform, very adaptable and easy to use. We focus on transient methods, because transient methods, in our view, are the future for thermal conductivity. And it's all about quick data, insightful data under representative conditions, very high sensitivity, excellent reproducibility. And, bringing that all together is really trying to make your life as a researcher simpler. We're trying to simplify thermal conductivity throughout this journey. We'll make it really easy for you to get the performance data so that you can focus on your iteration, your formulation development, your material selection, making it easy to get good quality data to support those different functions. Quick overview of our product line. This is not a commercial presentation. We're really going to focus more on the application space, but I just want to give you a little sense of the landscape. You'll see Trident in the middle here, featured quite a bit in the content that Arya will be presenting, and specifically it'd be the MTPS sensor. Trident brings together the three most prominent methods for thermal conductivity, and a lot of the strength of the product is based in that flexibility and being able to have some different options available to you. When we talk about thermal conductivity, it's really important to have more of a toolbox approach. Different methods have different benefits and biases or limitations. And something that's really important quite often for different labs is to have some flexibility, to have some different sensor options. And so Trident really accomplishes that nicely. You'll see a strong focus on the single-sided MTPS sensor, which is that stainless steel cylindrical sensor to the front right of the pyramid. You'll also see some reference to the TPS flex sensor, which is the yellowish sensor to the left. This is also great for concretes and really hard materials. You sandwich that in between two samples, and it provides a really complementary means of testing some of those harder materials. So Trident is a research grade product, and it is our most popular product to date. It's something that we'll spend a bit of time on explaining how that's used in different applications. To the left, I just wanted to mention really quickly, there is also a very budget conscious product offering with the thermal conductivity kit. So if you're bootstrapping a startup, or you've got a bare bones lab that you're trying to get going, and you just kind of want to get in the game, so to speak, the thermal conductivity kit is a very economical means of accomplishing that. That gives you the ability to run thermal conductivity measurements. You pair it with a Keithley power source measure unit. It has the data acquisition and analysis software included with the kit. It has a sensor, it has the software, it has a reference material. You just pair it with the Keithley and a laptop, and you've got everything you need to run basic thermal conductivity measurement. So it's a really good entry-level system if budget's a limitation. It doesn't meet the ISO standard for the TPS method. That would be the Trident product in the middle, but we can get into all those details on a one-on-one discussion. I just wanted to give you a little bit of a sense of the landscape of some different offerings available if thermal conductivity is something that you're thinking your organization needs to make an investment in the next few months to a year. On the far right is the TX product. We won't talk about that in this presentation as much. It's more for quantifying thermal touch. So whether something feels warm or cool, it's used heavily in textiles, sporting goods, soft lines, wherever the touch property is considered a critical performance attribute. I mentioned it really quickly in passing here because there has been some application of it on flooring. There's a researcher in Mexico, for example, that was altering the porosity of some ceramic flooring to try to enhance a warmer feeling for it. Sometimes it's uncomfortable to walk on cold surfaces. So there's a little bit of work done in construction materials, but I think thermal conductivity is the greater focus for most of us in this space. So we talked about Trident, brings together those three really prominent methods for transient thermal conductivity, all under one platform. This quote from Abraham Maslow really gets to the heart of the value proposition, and that it really is more of a toolbox approach that's necessary. Maslow writes, when all you have is a hammer, everything looks like a nail. And I think that's something that is easy to fall victim to in thermal conductivity analysis if you just are locked into one method. If you try to test liquids, if you try to test whether it's conductive or insulative materials, a lot of methods will do one or the other, not both. Testing different states of materials, if you're testing phase change materials, this is where it's really helpful to have some different tools at your, in your toolbox to address some of these needs. Really like this quote from Abraham Maslow, just for kind of capturing that at a conceptual level, the value proposition of Trident. These are some of the different sensors here, some schematic illustrations of them. And we provide this just to kind of relate a little bit the size of these different things and how that informs the minimum sample requirements for a measurement. So the far left is our most popular sensor. It's the one that will be featured most prominently in today's work. It's an MTPS sensor, modified transient plane source. That's a patented method by C-Therm Technologies. We're the only group that offers single-sided sensor that can test the full range of thermal conductivity. We're able to accomplish that with the novel use of a guard ring to ensure unidirectional heat flow into the sample material. Is this suitable for testing solids, liquids, powders, and pastes? A very versatile sensor. So you'll hear Arya talk a little bit more about this in his section, and I'll introduce him shortly. The Flex TPS also provides an excellent resource measuring thermal conductivity. One of the things I really like about the Flex TPS sensors, they also bring in some additional capabilities for testing thin films, for testing anisotropic materials. So if you're dealing with an oriented structure where the heat flow patterns may be different in the different orientations, through plane versus in plane, some really strong utilities available with the TPS. And it's available in different size formats. It's 6, 13, and 30 millimeter diameter sensors. The sensor we'll probably talk about the least today is the needle probe, transient line source. This is a sensor that's used for very sticky situations quite often. So think like polymer melts, anything that might bond to the other sensors and damage them in trying to remove a bonded material. Well, this is where the stainless steel sheathed needle probe is an excellent complement to our other sensors. And you can see it's quite a bit longer, so it requires quite a little bit larger volume of material. Okay, we'll keep moving along here. So these are some different accessories available with the MTPS. Top left is a powder cell. Same cell used bottom left. This is a adaptation for liquids. It has an O-ring in the bottom. It makes a nice seal. These are all accessories for the MTPS sensor. Top right is an example of one of our high pressure cells. So in thermal conductivity, really important to test under representative test conditions. Bottom right is something that might be quite useful in testing some types of insulation. You think of batting material, the level of compression of the material is something to report as part of the conditions under which the test was administered. So if you compress a material, you often push out the insulating agent, which is often air. Air has an excellent thermal insulation quality. It has a conductivity around 0.02. But if you densify the sample, that's going to increase the effective thermal conductivity. So this compression test accessory has a force gauge attached to it, and that helps you provide a very reproducible force load on the sample. There's no prescribed specific compressive force that's dictated with the device. What we really try to advocate in this space is, represent the true test conditions of the sample and the application. That's what you want to try to represent in your test setup. Here we see some different accessories for the Flex TPS sensor, TPS sample clamp, top left, one of our higher temperature versions of these sensors. We have them available up to 500 plus degree Celsius, but the standard ones are rated to about 80, 85 degrees Celsius. There are some different options available in terms of higher temperature, if it's so desired. Different sizes in the top right you see, and one of the powder test cells in the bottom right, all available with the Flex TPS sensor options. I mentioned those utilities earlier available with TPS. Slab allows you to test thinner sheets of material. There's the anisotropy test utility, and thin films, all available with these. Now, as we talk through some of these things, you're probably starting to wonder, well, how do I decide which method to apply in different situations? And that's where this method selection guide is really helpful. So I know AJ will be dropping that into the chat box here shortly. That's a free resource. It's available for download. I think it's about a 50-page comprehensive review of different thermal conductivity methods. It explains a little bit their principles of operation, what applications they are particularly recommended for, what are their limitations, and just helps you understand all the different factors you should be aware of in making your method selection for thermal conductivity. It does include some content as well on steady state methods. We don't do a lot of steady state work at C-Therm, but we know certainly in the traditional construction materials, you'll see reference to steady state data. I think Arya is going to address that a little bit in his discussion, but the resource guide does also provide some coverage of other methods, including laser flash and guarded hot plate, heat flow meters, etc. I want to mention a couple of our cooperation partners. We work closely with Metrovib and C-Therm. These are two French organizations that are global leaders in their respective fields. So Metrovib is the best at high frequency, high force dynamic mechanical analysis, DMA. A lot of work in rubber, polymers, composites, different application uses around those. C-Therm provides a really comprehensive line of thermal analysis and calorimetry products from TGA, DSC, TMA, etc. And very proud to work with both of those. They're both premium brands in their markets, providing really exceptional capabilities, pushing the boundaries of what's capable from a material characterization perspective, and producing a lot of value for their clients. We're happy to work with both of those organizations and representing them in Canada and North America. All right, and transitioning this over to Arya, who's the star of our show. I just wanted to leave you with a brief quote from one of our clients. I'll also ask AJ to drop in a link to our testimonials page if you're interested to check out what other clients are experiencing and working with C-Therm for thermal conductivity. There's a great resource. I think there's 60 to 70 different testimonials on that page. This is a nice one from NASA. We use it a fair bit because everybody knows who NASA is. Dr. Enrique Jackson just comments on purchasing one of our systems after seeing a demonstration of how fast and easy it is to operate, stating the instrument provides unequivocal results, provides the flexibility to test powders and liquids. In terms of satisfaction with the purchase, gave us a 10 out of 10, extremely satisfied. So that's a really nice quote for us from our friends at NASA, who are employing the MTPS method in the characterization of some of their semi-solids, powders, and all right. So with that said, I'm going to invite my colleague Arya Hakimian up. Arya is an expert in thermal conductivity measurement, application specialist here with C-Therm Technologies. He loves working with clients and helping understand what are the best and most appropriate methods for their different challenges that the client is facing. And really pleased to introduce Arya. Arya's done a great job curating a presentation here. It'll probably go a little bit past the hour. It's a really jam-packed presentation looking at all the different kinds of novel systems, composites, materials, and construction materials, and where thermal conductivity plays a really important role. With that said, Arya, I'll pass the baton to you, and I'll catch up with you on the Q&A session.
Awesome. Thanks, Adam. Hey, everyone. So like Adam mentioned, a lot of stuff to go through, so we'll jump right into it. Obviously, when we're talking about building materials, a lot of the focus will be on, the efficiency ratings, how well they are at, reducing costs. And a lot of that comes down to the energy consumption. So just to do a little bit of a kind of a preamble on that, especially over the last couple of years with, COVID's disruptions, particularly in the energy sector, I just have a few kind of stats to give. And really in 2020, there, across the board, there was large drops in the growth or, the demand of energy in many of the major countries. As an example, in the US, there was about 19 different energy companies that went bankrupt due to these changes. On the right, there's some information coming out of Europe, looking at fossil energy generation decreasing by 28%, nuclear demand dropped by 14%. Interestingly, though, and I like to include this for any of those who are interested in the renewables and kind of those more eco-friendly alternatives, even with the large overall decrease, renewable production did have a steady increase by 15%. So, that's always nice to see going forward. Now, while there was obviously a net decrease across the board, you need to kind of take into account some of the maybe things that may impact individuals more. So one of those notes is the cost of working from home. So many people, instead of working their 40 plus hours a week at their company at work, they've been transitioning to a work from home policy. And if you actually break down the energy costs here, while the overall scheme did decrease, residential energy consumption did show a massive increase, especially during those lockdown months in the early 2000, in the early 2020 months. And of course, with the changing landscape, kind of some research here showing about maybe 20% pre-COVID working from home. Currently, there may be around 70%. But as soon as even when we get through this pandemic, still a much larger increase of people likely to be continuing their work from home policies. So, of course, the energy consumption that you're going to be paying as an individual is going to be much higher when you're working from your house. So to kind of break that down and understand where are these costs going to really hit you, as an individual consumer, maybe someone who's, concerned with these overall efficiencies. This is a 2015 report, environmental agency out of the US, showing that about 50% of the overall energy consumption for residential comes from space heating and air conditioning. So this is really just the aspect of maintaining that temperature inside of your home. So obviously, as you can imagine there, the better the efficiency your house is related to the construction, the materials used, ideally those would be able to offset some of these energy costs and again, provide cost savings to you at the end of the day. So let's take a look at kind of a typical house. When we're looking at a building envelope, this kind of describes the skeleton of any building. And when we look at the heat loss, there is obviously some variability here, but approximately, from the roof, you can see about 25% loss, walls 35, windows and doors 25, and then the remainder going out the floor. So of course, depending on the build, the construction materials, these can all vary, but just to give you an idea, this is where your heat loss is coming from. And you can visualize this through different IR imaging. You can see on the right there, this is an image of a house that's partially insulated. So insulated half on the right versus the left. And the thing that you can see there is the brighter yellow or whitish areas are warmer. And that's indicative of, that heat really kind of transferring much quicker outside of that house and being lost to the environment. So this is where those insulation considerations come into play. Now, how does this heat transfer within a material? Well, there's really three primary modes of heat transfer that we'll take a look at. Conduction, this is the first one here. So transfer through a material. The classic example is you have that cast iron pan on a stove. You're heating that up, and if you don't wrap that in a towel and you go to grab it, obviously that heat is going to transfer through the bulk of that material. But similar things can be viewed, inside of a house as well, throughout the walls and the insulation barriers. Convection, this is another form. This really has to do with the transfer of heat energy by movement of currents, looking at air or liquid samples. But in a building, you can imagine if in between your drywall and the exterior, you don't have any kind of solid mass or material insulating, that convective airflow inside of the wall can actually transfer, again, heat from the inside to the outside if you're trying to maintain those temperature requirements. And then the last one there is a radiative heat or radiation. So this transfer of internal energy in the form of basically electromagnetic waves. And you've all experienced this if you've ever sat around a fire and kind of felt that nice warmth coming off in the winter time there. So these are the three primary modes of heat transfer. However, for us today, we're really going to be focusing in on conductive heat loss and how that occurs. So in insulation, these different types of materials are all kind of built with the purpose of reducing heat transfer. Common building insulations, they range, of course, but there's fiberglass, cellulose, foams, to name a few. And of course, these can all be in a variety of formats, whether they're a spray foam, kind of you see bundles or just kind of pieces that are placed in, or there's more rigid boards. lots of different aspects to these types of insulation, but again, ultimately here, the insulative capability is inversely proportional to the material's thermal conductivity. So thermal conductivity can really be viewed as again here, a key performance metric. And whenever you talk about a property like conductivity, you say, I have a good conductivity value, you need to put a little bit of a definition behind that, because obviously in this scenario here for insulation, lower conductivity values are what we're really targeting. So what is thermal conductivity? Not to spend too much time on this, but just to break it down really quickly, thermal conductivity essentially defines the rate of heat transfer through a material. If you kind of break it down, we have units of watts per meter Kelvin. The watts come due to the thermal energy input going through your material. This is obviously going through a given thickness of your sample, so denoted by meters, and then the Kelvin, so the K, as it's done across a material with a temperature differential. So this is really kind of the really quick high-level overview of conductivity, and we will discuss this in further detail in some of the coming slides. But when we're dealing with insulation and different building materials, a lot of the times we'll hear about thermal resistance, either R value or RSI. So just to explain what that is for those who may not be familiar, thermal resistance, this is an object property which is dependent on thickness. So conductivity is an intrinsic material property. Essentially, you can have we'll go into this a little bit further in a few slides, but it's irrelevant of the object itself. But thermal resistance, on the other hand, we can see that this is calculated by dividing a given thickness of material, so L, by your conductivity value K. So it takes into account the thickness of the material in question. Mentioning that there are kind of two different, versions, let's say, of thermal resistance. So R value, this is the imperial units, and then RSI, which is the metric system. So always good to take note of which one is actually being mentioned here. In both cases, though, the higher the value of your R value or your thermal resistance, this is a better insulative material or a higher performing insulation. To convert between the two, there's just a conversion factor. So if you multiply your RSI by 5.678, you can get to R value. Similarly, going the other way by dividing. So there is ways to convert between them quite easily. So just a couple examples here, maybe kind of a little thought experiment. But so thermal resistance, if you're trying to modify this can really be done by two ways. We notice that resistance is equal to the length or the thickness of your material divided by conductivity. Therefore, increasing your R value, your insulative performance, can be done by either increasing the thickness of the sample or decreasing K. So in this example, we're just looking at a sample 1 and 2. Both of these are presumed in this scenario to have the exact same conductivity. So it's the same material, but we're noticing that one has twice the length or twice the thickness of the sample. If you were to plug this in, you would notice that solely based on the differences in thickness here, the sample number 2 has a much higher R value because we're taking that conductivity and dividing it by a larger number in the denominator. So obviously this is going to give you that change in R value. Up next here, we're looking at taking a look at the thermal conductivity changes in your thermal resistance. So in this setup, we have two different samples. And in this case, we're actually looking at the effect of the conductivity value changing. So kind of similar in idea based on the differences in the thermal conductivity in this scenario, the lower thermal conductivity is going to result in a higher R value. Now, Adam did mention earlier, there was the mention of steady state. Obviously this is widely adopted in the industry as a kind of a long time standard. Steady state heat flow meters really benefit from the use of the ASTM C518 methodology. It's a very high precision device, excellent for those lower conductivity samples. Of course, there are a few drawbacks here. If you're going to go into those, generally a little bit more rigid sample size requirements and geometries, longer test times. You are measuring over a much larger area based on the sample requirements, so you lose a little bit of that spot-to-spot variability that may be present in a material. As generally a steady state setup shown on the right, you have a hot plate and a cold plate with your sample in between, and you're measuring the heat flow through that material once it reaches steady state conditions. So obviously we're really focusing in on different transient methods. Adam kind of went over these a little bit earlier there, but on Trident, 3 different options, all of which really provide much faster test times. As an example, the MTPS, you get your measurement times in about 1 to 3 seconds, depending on the samples that you're working with. They provide options for more representative testing conditions. These sensors can be placed in varying temperature, humidity, pressurized environments for this type of test. And really, at the end of the day, can really act as a complementary method in tandem with some of these steady state methodologies. Because of the rapid testing aspect of transient methods, it can really lend itself quite well to dealing with high sample throughput, where you're dealing with large sample volumes. You need to get rapid testing. Everyone knows time is money at the end of the day. So whether you're in the R&D stages, QA, QC, these transient methodologies can be adopted to really help speed up your screening process, find the materials that are generally more conductive or less conductive depending on the end use application. And then obviously later on down the road, if the industry standard requirements need C518 testing, then you can work with those in tandem. Just as an example though, this is some measurement comparisons that were taken on a few different foam insulation samples. We notice here heat flow meter data in orange, MTPS data in blue. Across all tested samples, again, see a couple various foams and then the NIST DPS standard, thermal conductivities were well within 2% of each other. The biggest differentiator between these was the fact that your heat flow meter test times were generally on the order of an hour or more, whereas your MTPS, we're able to get 5 back-to-back measurements in about 5 minutes. So really kind of just highlighting those speed differences between the methodologies. All right, so now kind of onto the interesting stuff. These are a few case highlights. A lot of these are actually just recently published, within the last few months or last year. So just diving into some different ways the sensors, the MTPS in particular, has been used to do some of these kind of novel characterizations. This first one, this is a study coming out of Vietnam and Singapore, joint study on applications of using material, or in this case, pineapple waste, for the development of an aerogel sample. So really using these bio-based engineering applications and reducing and repurposing otherwise waste materials in more of an efficient way. So the idea behind this study is really to reduce the environmental impact of some of these waste products. So you kind of break down global greenhouse gas emissions by sector. We see that the agriculture industry accounts for about a quarter. If you kind of dive into this, a lot of that number, or a lot of the portion of that, really comes from the fact that you have to burn off a lot of the waste products that aren't used. So you can imagine that if you're taking the product out of harvesting it, not all of that material may get packaged up and sent to the grocery stores around the world. Some of that, it goes through different processing techniques, and there can be an associated amount of waste that is present. The one that they looked at in particular was pineapple waste, and if you kind of dive into it, it was kind of surprising to note, but you break down a few waste sources, so the crown, the peel, the seeds and core. In some cases, you get about 50% of the product itself as waste. So when you imagine going to the store and you buy that inside of a package, all peeled and taken care of for you, what you're not seeing is where did all the other pieces go? So in an attempt to reduce some of that waste, this group took these pineapple fibers, known as PFs, they mixed them with a PVA solution, did some varying thermal and pressurized treatment, and essentially created these aerogel blankets that you can kind of see rolled up on the right there. Now, some of the results that were obtained, you can see up top the SEM imaging at different weight percentages, so 0.5, 1, and 2% weight loading of the pineapple fibers. As you can kind of imagine, the increasing fiber concentration, this essentially resulted in a decrease in overall porosity. Basically, the more of that fiber was present, the more material was available to fill in that interstitial air, again, pushing some of that air out. And as Adam mentioned earlier, air is a really great insulator. So if you have more material there, more methods or more routes for that heat to transfer within the bulk, that will result in a net increase in conductivity. So what they noticed is the lowest PF concentration, so the 0.5, was denoted with the lowest effective thermal conductivity measurement, and therefore the most insulative in nature. So they're able to conclude that just kind of based on these initial results, these pineapple fibers are, a great option, an eco-friendly alternative building block for some novel insulation materials. They exhibited extremely low densities. There's also some studies that weren't presented here, but good mechanical strength, and obviously the metric we're interested in is the low thermal conductivity. And of course, this is just on one product, pineapples. So you can imagine the other potential sources to reduce some of these high waste areas and repurposing them for similar applications or even other applications in the future. So great area of investigation done on this bio-based insulation. This next study, this was done on phase change materials for thermal energy storage in buildings. This is coming out of works done in China. And we'll dive into this one. This one, they did a lot of interesting studies on PCMs. Now, if you look at kind of a generic PCM life cycle, if you kind of start out in the solid state, you increase the temperature, that PCM will absorb that thermal input and then begin to melt. As that continues, it enters into its liquid state. And if you kind of repeat the cycle there, once the temperature starts to decrease, the PCM releases that thermal energy to the environment and then goes back into the solid state. So that's essentially the cycle that it will run through. However, traditional PCMs, while they are, they do have these very unique qualities, they do tend to suffer from liquid phase leakage, limited available latent heat, and generally poor thermal conductivity. So what these researchers were aiming to do is to improve the overall performance of this capric stearic acid, which was their PCM, using a montmorillonite substrate to act as basically an encapsulant to help contain that PCM during the transition. As well, on top of that, they wanted to incorporate graphene to enhance the thermal conductivity properties of this sample. So it was twofold, to reduce some of the leakage effects and then also improve on the thermal properties. So we can see some of the SEM imaging on the right there. The top two, we see the MMT structures. When it gets a little more interesting is when you look at the C picture there, middle left. That's the incorporation of the PCM MMT composite. You see the graphene monolayer to the right of that. And then on the bottom, what they're actually finding is that when you incorporated all of these materials together, it's kind of small and writing there, but smooth and dense surface. So that's a really good indicator that that PCM is going to be well contained inside of that composite material. And what was really interesting is in the image to the right, after 300 thermal cycles, the morphology remained fairly constant there. So when it kind of went through that melt to solidification cycle 300 times, it still maintained its form quite well. So really kind of lending itself to really good thermal cyclability. And then we kind of look at some of the results that were obtained. First on the left here, thermal conductivity. As was somewhat expected, you can imagine that as you introduce new components, even just going from 1 to 2, so 1 was just your base PCM, 2 noted here by the introduction of the MMT substrate. MMT did note a marked increase in the conductivity measurement. And then the following 3, 4, and 5 are just continual increases in the amount of graphene that was added. So as would be expected, you can see this clear trend in increasing thermal conductivity. So what they actually did was once they prepared these samples, they did various thermal imaging. So on the right here, so maybe looking at the A column, looking at the 242nd mark, you can see that through the increased graphene content, that material goes into that liquid state much quicker there. So going again from the change from blue to that reddish white, you'll notice that the highest concentration graphene obviously was able to transfer that heat much more efficiently throughout the bulk of that material. So in conclusion here, they were able to find that the CA, SA, MMT composite PCMs, they demonstrated excellent cyclability. They did a lot of study on the DSC, various calorimetry properties as well that aren't really highlighted herein. Phase change temperature was in an ideal range, and they did note the increased higher latent heat. So that latent heat is actually an important factor here when you're considering the thermal management applications, or that heat storage, I should say, within the building envelope if you were to incorporate these. The graphene additive really improved the heat transfer efficiency. So while you do need to maintain that heat storage, you do need to make sure that it is transferring efficiently within the bulk, and that's what the graphene really showed and accomplished here. And at the end, they concluded it was exhibited great promise for application in a novel building material. The images on the right were actually just them taking that PCM, the highest graphene weight loading, and then adding it at different weight concentrations inside of a brick and a mortar, and then doing some various thermal imaging studies. And again, what they were able to find is based on that higher latent heat of capability of the PCM, it really allowed to reduce the that heat loss that was occurring on heating and then subsequently on cooling inside of that building brick sample. All right, so this next one, this is on a characterization of earth mortars, stabilized with a very interesting additive. So it's an air additive, and we'll get into this. This is a paper that was published by a group in Brazil, and this was actually presented at the ICBBM. It's an international conference on bio-based materials this past year. So an earth mortar, first looking at what is a mortar, these are the paste-like materials that kind of help bind those building block materials. So you can see in the image on the right, the mortar is that paste that you'd apply in between the bricks in order to kind of connect everything together. Now, earth mortars in particular, these have gained attention because, of course, it's an environmental friendly alternative using more naturally occurring materials, lower environmental impact that still have really great efficiencies and durability ratings. If you look at any type of material consumption being used for the production of anything, you kind of see in this kind of the graph in the bottom left, there's a lot of considerations to take into account. So how much water is used in the production or the extraction of that material, the toxicity levels, the effect on climate change. So you can really kind of make a well-rounded map of what that material is going to introduce as an environmental impact if you're deciding to use that in your process. So to really help improve on some of those aspects, these earth mortars, they were mixed with the following ingredients you can kind of see on the right there. So fly ash, natural sand, cement, to name a few. But the one I want to draw your attention to is the EcoFoam AEA. So this is a very interesting material that I'll kind of just talk about a little bit here. So an AEA is an air entraining additive. What this does, it's an additive material that helps introduce these microscopic voids or air bubbles inside of the sample as it cures and dries. So in this study, they had 4 different earth mortars with varying concentrations of that AEA additive. And what they're aiming to do is obviously these thermal characterizations and also some structural and mechanical testing as well. From a density perspective, or you can kind of correlate that to the air content as would be expected, increasing that AEA additive decreased the effective density of that material while increasing the total air content that was present. So what that did as far as an end result on the dried product, you can see some SEM imaging there, just denoting that you were getting these micropores present inside the sample bulk, increasingly more and more with the increasing AEA content. They did note there was significant cracking, as you can kind of see in all of these SEM images. So cracking, this is something that needs to be taken into account. But from a thermal aspect, at least, we can see that basically going from that top right, which was the earth mortar with no AEA additive, all the way down to the highest concentration in the bottom left, you do get that noted decrease in both, in this scenario, conductivity as well as effusivity, kind of trending in the same way. So in conclusion, they were able to use this AEA and this earth mortar mix to increase the air content by quite a significant degree, with a corresponding net decrease in density. This all added into a corresponding improved insulative performance, so increasing by, it was upwards of 23%. So again here, increasing insulation performance means decreasing conductivity values. And as a note, just wanted to mention this, they did find that at that maximum loading, because of the structural aspects, the highest weight loading did decrease the overall mechanical strength by 89%. So of course, there's various aspects you need to consider when developing these types of materials. We're obviously focused on the conductivity side of things, but there are a variety of other variables that need to be taken into account as well. This next is on a ceramic brick used from a zeolite, poor rock, and sawdust mixture. This is again another study where you're taking these otherwise unused or perhaps waste products and repurposing them. This is from a study coming out of Hungary. And in this work, obviously, we kind of looked previously at the mortar, so what was keeping those bricks together. Now we're looking at the bricks themselves. So traditionally, a brick was denoted as a material that was composed or made up of clay. Nowadays, varying material compositions are defined as bricks, really any kind of building block. But ultimately, the goal of this study was to reduce the use of clay while simultaneously contributing to a safe disposal alternative of some of these waste products. Clay harvesting does deplete natural resources in those areas by quite a significant degree. So there are actually some areas around the world which will put limitations on how much clay can be extracted from a certain area because of the negative environmental impact. So in this study, you can kind of see the flow chart. They are basically mixing this zeolite material and sawdust, going through this process, and then characterizing the end samples that were developed. So the production process, again, it involved taking those powders or those materials and ball milling them, creating this mixture, and then pressing them into these cylindrical brick-like samples. And you can see here that they went through varying compositions. So your control, which was all zeolite, sawdust, and then slowly started gradually increasing the amount of sawdust that was present inside the overall sample itself. From the results, again, we kind of see some SEM imaging on the left there, but the story that we want to really take a look at here is the varying sawdust concentration was noted to have a net decrease in the effective conductivity values, as kind of seen on the right. But they're also firing these bricks or sintering them at different temperatures. So this is once the brick has been made, you heat it up, basically dry it, and then take that out and then test as needed. So there was also an influence that we can see quite notably on the influence of the sintering process on the effective thermal conductivity results as well. What they were able to conclude was the sawdust essentially acted as an effective pore forming agent within the sample to really help produce these lightweight bricks. The increased pores, as we know, again, increasing pores, increasing air, therefore improved insulative performance was noted here. Again, they did varying other tests. One of the mechanical limitations, they found that optimal sawdust loading was at 8%. When you kind of take into multiple factors, that was their optimal weight loading. And the sintering at the lowest temperature, so at 950 C, that actually resulted in one of the more fragile end products. So they were aiming to basically use a high sintering temperature with a specific weight loading of sawdust to get their optimal performance out when you take into both thermal and mechanical considerations. And then this one here, this was a neat one that we found. This is on a brick fabrication using a 3D printed technology with an aerogel additive. So this is some work coming out of the United States, University of Akron. This one, for any of you who like playing with Legos, or if you have kids that like playing with Legos, you'll get a kick out of this. They basically designed these 3D printed materials with these Lego-like structures. And the idea here was generally, while very insulative in nature, pure aerogels can be very brittle, damage quite easily, sensitive to moisture. So incorporating the aerogel additive into the polymer matrix in this fashion, you're able to maybe fine tune and tailor those properties to what's needed as your end use. So you can see the overall process that was used here in the SLA printing technology. They had various different materials, so polyamide, aerogel SLA, and epoxy, varying concentrations across the board there you can see on the bottom. A very well done paper, I will say. If you have a chance to go through this, they had a lot of different studies and aspects of the material done. They looked at drying process, post-curing with different solvents. Obviously, a lot of considerations were taken into account here for this study, but at the end of the day, looking at kind of those final thermal conductivity results, and again, kind of some supporting SEM imaging on the left, they were able to see that in all cases, fairly low thermal conductivities were obtained. Of course, the PI aerogel monolith denoting with the lowest effective conductivity. As you increase that polymer component with respect to the aerogel amount, those properties do change, and we see that net increase. But across the board, fairly low conductivities were observed. In conclusion, they were able to really highlight the capability of producing these modular polymeric aerogel bricks with this 3D printing technology. So lots of interesting work coming out with 3D print AM processes. The aerogel contributions really accounted for that improved insulative performance, whereas what they were able to show, again, not noted here explicitly, but the SLA resin really provided a structural strength that benefited from the mechanical side of things. And then just kind of some, again, a lot of these papers all having these IR or temperature imaging images done, and we kind of see one there on the right where they stack some of those Lego-like blocks together. And then finally here, just before we wrap up, this is a kind of just an internal application highlight on some cements and concretes. All of those papers that we just kind of went over, those are all using the MTPS method. So just to kind of take a look at the TPS, where it can come into play, really useful if you are dealing with a material that's hygroscopic in nature, so maybe would absorb or react with water. Some materials may require a contact agent with MTPS, and therefore TPS can be a viable alternative if there's some compatibility restraints. It has an overall very flexible design. It's a little more complex to operate than the MTPS, but still going to provide you measurements much faster than those steady state counterparts, as well as it does conform to ISO 22007-2. So just kind of a quick data set that was collected here. So 10 individual measurements taken on this lightweight concrete sample, average value found to be about 0.52 watts per meter Kelvin. And you can kind of see the overall accuracy and reproducibility here, noted with those plus minus 5% grid lines. So with that being said, I just squeezed it in right under the hour there. I just want to say thank you for joining our session here today, either with us live or if you're watching the recording. My contact information, my email there is on screen. If you did have any questions, always love to have those one-on-ones externally. Also feel free to reach out to me on LinkedIn to continue these conversations. I will just kind of mention a lot of additional resources available on our website. We have a massive library of previously recorded webinars, tech libraries where you can actually find some of these papers that are using the MTPS or other transient technologies, and kind of see how those are being used by groups in the academia or industry. And also, I believe AJ might be putting some of these links in the chat as well, but if you did want to take the next step, perhaps book a video demo. This is something that we're doing, these online virtual demos, really being able to kind of reach you when we're not able to travel. Also, complimentary sample demo testing is an option, or if you're just simply interested in a quote for Trident, also able to assist there, and you can find that contact information on screen. And lastly, just a plug for an upcoming webinar. This is coming up in a couple weeks there, improving heat dissipation of submarine network repeater enclosures with a novel filled material. This is actually be done with our guest speaker from Martin's Rubber, Dr. Isaac Watson. So definitely if that's of interest, just wanted to plug that in for you guys as well. So with that, I'll end my portion there. I'll go into the Q&A session, throw it back to Adam. But again, just thanks for joining, everyone.
Excellent. Thank you very much, Arya. That's a wonderful job. Quick blitz through a broad range of novel materials for construction. Really enjoyed your presentation and the way you brought those different applications together. Thank you very much, Arya. That's a wonderful job. We are going to move to the Q&A session, but we will stop the recording at this point. So for any of our audience that will jump off here, I want to say thank you as well for taking an hour with us, and really appreciate your interest in thermal conductivity and some of the work we're doing with clients in this field. Hope you found it a valuable use of your time, and just to echo some of the comments Arya made, would certainly be very happy to pick up this conversation one-on-one. If you'd like to book a consultation, if you'd like to see a private demonstration of how the equipment works, these are great resources that can help you understand if it's, for example, an appropriate solution for your particular testing challenges. Again, our raison d'etre in life, our reason for being, is to simplify thermal conductivity testing for our clients. And so if we can be of any service in that regard, we would love to be a resource to your group. Okay, so thank you again for any audience members jumping off here, either in the recording or live session. Appreciate your time, and we'll now proceed to Q&A.